Let's go on to 14.7. This is on extreme values and saddle points. So this is analogous to Calc 1, where you get into max and mins, maximum and minimums of functions on an open interval and a closed interval. So we will define this now in 3D, and how it looks. It's a little different, but it's really the same concepts, which kind of makes it nice as we go through stuff. And then we'll do. Remember in Calc 1, you had the first derivative test and second derivative test. Well, we'll develop similar things. We're going to develop actually what's called the second partials test, and it'll be used to find max and mins and saddle points of functions. So that's where we're heading. First, a number of definitions. Okay, first definition is this. So a point AB is, let me write that a little better, a point AB is minimum or maximum. I'll spell it out this time. So minimum or maximum. We'll just abbreviate min-max from here on out. In a region R, and right now we're not defining it to be open or closed or anything, we're just saying it's some region. And then you have two cases. So the minimum states this: if f of AB is of course less than or equal to f of xy for all xy in R. Probably leaving off little details like R is in the xy plane, that kind of thing, but it's kind of implied there. And then maximum, if f of AB is of course greater than or equal to everything else, f of xy for all xy in R. Okay, so that makes sense. So basically you have some region. Let's just do a little diagram here. So you have some surface like this, a usual generic surface. And then you have some region down here in the xy plane underneath the surface R. And then you have all these points that go up to our surface S. And so if this point down here, AB, is maybe greater than everything else, then it's a maximum. So we're going to go up to that surface and call it a maximum. So that's, and then of course, it could be, and so this is one of those things where it could be on the boundary or it could be inside, and we'll define later whether it's open or closed. So the extreme value theorem is just like Calc 1. So just a quick reminder, extreme value theorem, let's just do this off to the side here. I don't have this in my notes, so we'll just do this just as a reminder. So this is single variable. Let's just do it like this. So in single variable, extreme value theorem basically is saying this. We'll just do it by diagram. If you have a closed interval from A to B, then there's guarantees for a continuous function, a minimum and a maximum on that closed interval. So let me just draw this like this. Okay, so if you go like this, like that, then right here at the end point, it may mean nothing. Let me see. I didn't draw that quite like I wanted to. Let me draw it a little differently. So I wanted it to kind of max, and then kind of make it go max, and then min will do down here like that. So on the interval, there guarantees a maximum and a minimum, and it may occur at the endpoints. So right here, f of c is clearly a maximum, but the minimum looks like it's going to be right here, which would be your f of b, and that occurred at the endpoint of the closed interval. So the extreme value theorem says that it's guaranteed that it is achieved a maximum or a minimum on a closed interval, and it may occur on the endpoint. So here, f of c is a maximum, and here on the endpoint is the minimum. So that's what it basically says. So this is what's being stated for a on a region, right, in the xy plane. It'll be the same type of statement, but for a region. Okay, so that's single variable stuff. Let's go back to the extreme value theorem in 3D. So this is what's called the extreme value theorem. So we're going to let f of xy be continuous. And that's one of the hypotheses, of course, over here is that the function has to be continuous. So you can't have it like stop and start kind of thing. So let f of xy be continuous on R. And I'll spell this out a little more carefully, in the xy plane. R, now in this case, just like in Calc 1 where you have the closed interval, R must be a closed and bounded region. So that's the difference. So R is closed and bounded. Okay, then that's where you have the existence of the max or min. Then there exists a minimum and maximum on R. And what you would say in this Calc 1, you'd say it may occur at the endpoints. Well, if we don't have endpoints, you would say it may occur on the boundary. So you say it may occur on the boundary. So you got to test the boundary. So like if you're given a circle, you have to, you'd substitute, well, we'll get to that, but you'd substitute in the values that make it a circle and you test the actual boundary points. Okay. Not going to prove that or anything. There's plenty to do in this section just by applications. Let's go to the next definition. Now we're going to talk about local and relative min or max. So this is the definition of local or relative minimum or maximum. Okay, so same kind of concepts as before. So let f be a function defined on R containing the point x naught, y naught. Okay, then we have two, we'll just define the two cases. We have one. So this is the local, what I do first, we'll do local minimum. We're sticking the minimum first. Local minimum is basically its minimum in a delta neighborhood, right? So you don't put an open interval around it, you put a delta neighborhood around it. So you say f of x naught, y naught is less than or equal to f of xy for all xy in a delta neighborhood. Remember the abbreviation for delta neighborhood? And it's open, right? A delta neighborhood is an open circle, basically. Okay, so local maximum, you just same idea. F of x naught, y naught is greater than or equal to f of xy for all xy in a delta neighborhood. So remember, a delta neighborhood is basically this idea, right? You have, I can do a little circle, so you have the circle, and so at some point or other, it's the maximum or minimum within that delta neighborhood. So that you can put a value around it, and then it's the max or min. And so those are those little bumps and dips in the graph, right? Just like in the single variable, it's that and that. Those are what we refer to as your locals. And then if you put a closed interval on it, it might be the max, absolute max, or absolute min. Okay, so that's what we're looking at. Okay, so that's your delta neighborhood, just as we defined before. You may want to look up that stuff. You may want to look up open and closed. Where did I put that? Okay, so you may want to look up closed and bounded regions and delta neighborhood. You know, just to remind yourself what those really say. For the most part, we're using the intuitive concept of that, of what those are. So let me draw a little diagram. So we have our surface like this. And so you have your region down here, which, let's see. Well, I'm just looking at some region. So you have some region that can be open or closed for R. So R is down here, but then in your delta neighborhood, let's just copy that, put it here. Then it's the max or min in that delta neighborhood. So if you in there, then you have some point, say here, that is the the maximum or minimum value. We'll make it a maximum because it's easier to draw. So that value up there on the surface is maximum. Like suppose, right? And you can picture the graph bouncing or whatever. Up on the surface, it may, it's going to be kind of look like this, maybe. Although, let's make that dotted. My little dots here are kind of blessings and curses at the same time because it takes more time, but it looks better. So up here might be what the delta neighborhood looks like up there, and then that point is your local max or min. Now, over here, it might be a bigger, larger point, or might be a minimum, might be bigger than this one, but it's basically a bump or a dip in the graph around that point. Right? That's what you can do. Okay, so that's what we refer to as your f of AB as local. So it's a local max or min within that delta neighborhood. Okay, so that's our concept. All right. I'm going to move this to the side, and then we can define our critical points over here. Okay, so over here, well, I'm just leaving some more space up on the. So there's more space on the notes. In other words, let's define next the critical point. Similarly defined as in Calc 1. This class actually has more in common with Calc 1 than Calc 2, actually. Like the progression through the course. Okay, so critical point x naught, y naught for a function z equal to f of xy is this. Okay, so we say x naught, y naught is a critical point. And it's an actual point. It's like x naught, y naught. In Calc 1, I often mess up and say critical value, even though you can say a point, even though it's just a one value. But this is an actual point. So I try to be consistent. It's a critical point. It's actual x naught, y, xy. So x naught, y naught is a critical point. I'll just say in a region R or in xy plane. Oops. Let's say it like this: xy plane. Wherever the function f is defined on, f of xy. If 1 partial of f with respect to x at x naught, y naught is equal to 0, and partial f with respect to y of x naught, y naught is equal to 0. Or 2, either partial fx of x naught, y naught or partial fy of x naught, y naught is undefined. So either one can be undefined. So what that's basically doing, and I'll talk more about this a little later. I'll do that. But basically what's happening then is so the partial of f x is the slope of the tangent line in the x direction. Fy, slope of the tangent line in the y direction. What that gives you is a horizontal tangent plane. So it gives you that horizontal tangent plane at a point. Okay, so this implies basically horizontal tangent plane. I think I usually demonstrate this a little more when I'm actually able to show you a piece of paper on a surface, kind of stuff. But that's what's basically it implies. And this, for 2 undefined, those are the cusp concepts. So I'll just maybe say, I'll just make a little triangle here. So I'll just say like a cusp. I mean, it really is a cusp if it's a cusp, but that's what you think of. Is it is a point like in 3 space and 3D? It goes like this. Well, that might go up in multiple directions to give you that cusp. It's going to be the function is going to be undefined there, but it still might be a local min or max. We don't really have to know yet. We just need to know that it's a critical point. So what's going to happen basically is you're going to be solving a system. So right here, this right here is going to be a system of equations. Okay, so that'll be a system. Let's just leave that off. I'm talking too much. Let's continue. Next theorem, same thing as Calc 1 again. And I'll leave off. I'll spare us all the little details. But basically, relative extrema only occur at critical points. So if there's a critical point, well, no, if there's relative extrema, it's a critical point. If it's a critical point, it may or may not be anything. We don't know. So it's only one direction. So, and let me spell that out this time a little more carefully how I have it written in my notes there. Oh, I was going to highlight that too. I don't want to take away from this one. This one is the other big, important piece to it. Those are what you're looking for. That may be like a cusp or something. That's or a corner, but the corner could be something interesting. It's still, but you got we'll have to test for it, which we have ways of testing that. Okay, what was I going to tell you? Okay, so so this is an if then. If x naught, y naught is a relative extreme point, then it is a critical point. So it must be that direction. The converse is not necessarily true. Okay, so let's write that down. The converse is not necessarily hold on, I messed that. Okay, you have to test it. So another way of saying this is relative or local extrema only occur at critical points. Okay, so that's really the idea. So that's what we do. We go find the critical points, and then we'll use tests or some sort of analysis to figure out if it's a max or a min, or local max or a min. Okay, let's look at an example of this without our test, second partials test. This one's pretty straightforward type of idea, and we already know the answer. You'll see what I mean in a second. So find all relative extrema for f of xy equal to 1 plus x squared plus y squared. Restricted to r equal to xy such that x squared plus y squared strictly less than 4. All right, so this is not closed, so we're not applying the extreme value theorem or anything, because this is an open region because of the less than. So you're talking about a circle. So we're not going to get to those endpoints. All right. So anyway, when you look at relative, you'll see what I mean. So what you do is you look at the partials. Okay, so you calculate or find critical points. We'll call them CPs. Okay, so back here, we'll call our critical points CP. In Calc 1, I call them CVs for critical values. It doesn't really matter. I'll get what you mean. So critical points, we do the partial of f with respect to x. That's just 2x. And then you do the partial of f with respect to y. That's just 2y. And then you basically solve that system. Now this one's pretty easy when you solve this system, but the process will always be the same. Okay, so that implies, pretty obvious, 0, 0 is a critical value. Okay, so the only critical value. All right, so basically, without the second partials test, this one's simple enough. You just analyze it. So essentially, it's the only one. So let's draw the picture. Like we can draw the picture and argue why it must be a local minimum. So we draw the diagram, draw the picture. X, Y, and Z. So we know this is paraboloid shifted up 1 unit like this. Okay, so we know what it looks like. Nothing real special. And then it is it's defined on a region like that. There we go. Close enough. Okay, so there's my region R. All right. So basically, we argue that 1 plus x squared plus y squared is greater than or equal to 0 for all x, y, and r. And because this is positive, this is positive, this is 1, so it's always a positive number. And greater than 1. Actually, I meant to write that. Okay, this is always greater than 1 for all x, y, greater than or equal to 1. Because you're adding positive values. So since 0, 0 is the only critical point, and f of 0, 0 is equal to 1, that has to be a local extrema. So it is a local extrema. All right, so there's not that much else to discuss on this one. It's just showing that it does work. We can also state that f of x, y, just another way of saying this, is equal to 1 plus x squared plus y squared is greater than 1 if x, y does not equal 0, 0. Same thing as basically above. So therefore, 0, 0 is a local minimum. It's the smallest value. And it's actually the absolute. On that, on the region. Well, for any value of R. Okay, so sometimes you just argue it based on the algebra. There's really not a whole lot else to look at. In Calc 1, you might be able to show it's always increasing, but we really don't have that yet. But you could argue that x squared plus y squared are positive values that you're always adding together, so it has to be greater than 1. So 0, 0 has to be the smallest one. All right. So next, let's define the second partials test, and then we'll probably go ahead and do another video on the examples. All right, so this is what's called the second partials test. This is what we'll be using. So the second partials test. All right, so let f of xy have continuous second partials on R. R is a subset of R2, which is the xy plane. We need to define something called the discriminant. The discriminant d of f is defined to be this. It's d of xy is equal to partial f, second partial of f with respect to x of xy times the second partial of y, second partial of f with respect to y of xy minus the mixed partials squared. And as you know, it doesn't matter the order you do the mixed partials, but usually you just do x then y. Okay, so you can leave off the evaluated part xy and just remember it like this: fxx fyy minus fxy squared. The other way to remember this one is d equal to the determinant of, here's the determinant again, fxx fxy. So you just do x then x, x then y. Then you do f y then x, and then f y then y. All right. And then when you do that, you get fxx fyy minus fxy fyx. But mixed, when a function's has continuous partials, then mixed partials are equal, and you say that that's just xy squared is usually what we pick anyway. So it's minus xy squared because there's two of them. Okay, so using that, we have this next piece. If AB is in R, is a critical point, and then R is open. So we're not looking at the boundary in this case. That we basically have to test the boundary itself. So R is open. So as a critical point, R is open That is, so I did it, that is. So that is actually, it's a critical point, and this has to be the case. Partial f. So it's the case 1. I'll just say and. So this is case 1 only. F x a b equals 0 and f y a b equals 0. So it's the horizontal tangent plane. Okay, then we have 3 cases. So this is, when we talk about a critical point, it's this case. If you have undefined, you have to do your own thing. You got to analyze it yourself. All right, so then, okay, so 1, if the discriminant is greater than 0 and fxx is greater than 0, then f of AB is a local minimum. Okay, so that's what you do. You calculate the discriminant and look at the second partial as well. You evaluate these, of course, at the point. So then if the discriminant is positive and partial fxx is less than 0, then that's a maximum. Then partial f of AB is a maximum. Okay, and in both cases it's a local. So I'll just put local here. Okay, 3, if the discriminant is less than 0, then that point is a saddle point. Then AB, f of AB is a saddle point. So that's like saddle point would be like the Pringle or it's hyperbolic paraboloid. So the hyperbolic paraboloid is the saddle point situation. So you have going up like this and down like this. So that's the saddle point case. All right. Then last one is if it fails, basically, is the one you don't want. So if the discriminant is equal to 0, the test fails. You got to use something else. We just say the test fails, and you need to just basically analyze it. Now these are all for nice functions. So f has continuous second partials. So this isn't the cusp situation like I showed above. Those you have to analyze individually, on their own and see what's going on. But this is this is like analyzing a polynomial, right? So everything's nice and smooth and dandy. Then you can just apply this test. So there's enough going on here that we don't get too crazy with the examples. Because just solving the system itself, calculating the discriminant, there's a lot of stuff, step-by-step process to go through. So we focus on that. There's enough to focus on there. Okay, we will do examples next. I have a number of them to do, including some applications.